So last week we talked about exponential growth functions. This week we're going to start talking about exponential decay functions, and it's basically the same idea. So an exponential decay function has the form y equals ab to the x, where a is still greater than 0, and where b is between 0 and 1. So basically what you're going to see is that b is a fraction. So the base b of an exponential decay function is called the decay factor. So when we talk about exponential growth functions, remember last week, exponential growth, those were the functions that on the xy axis, they started low and ended up going like this. Now if you flip it over the x-axis, it's still in theory a growth for some problems, but in general we're going to say this is exponential growth. And then exponential decay will look more like that picture right there. I'm just going to draw it again. Exponential decay looks like this. So it starts high and goes low, and it grows slower and slower, basically. So we're going to use the same method to graph this as last week, where you're going to test at 0 and at x equals 1, and you're going to find this pattern where you really don't have to do a ton of math. So let's take a look at example 1. We're going to graph the function, state the domain, and range. So just like last week, start with x equals 0 and x equals 1. Remember, when you plug in 0 here, that's just going to make your coordinate be 0, 1, because anything to the 0 is 1. Likewise, when you plug in 1 here, if that was a 1, you just have whatever the base is, so it's 0 and 1/2. So really not a lot of math that you have to do there. So when we graph this, start at 0, 1, and then it goes 1 1/2. So now it's easier to still draw from the asymptote. The asymptote has not changed here. Exponential decay versus growth, your asymptote is still going to be that y-axis unless it's transformed or shifted. So I usually start drawing from the asymptote, so now I'm going to draw backwards. So it's going in that direction. So this is my exponential decay function, where my domain is still -infinity to infinity, because all values of x work. And my y minimum, so if you think about your y minimum, it starts at 0 on up, so even though we're kind of looking at it backwards in terms of our range, it's still from 0 to infinity, and the asymptote is still y equals 0. So just like last week, we can change these, we can stretch them vertically by adding a number here. So we have y equals 2 times 1/2 x, and we're going to see this doesn't really change the domain, but it'll change those initial 2 points. So just write this again so it's in vision. So 2 times 1/2 to the x. So this is the same thing. You can memorize kind of like the rule here when x is 0 and when x is 1. So when x is 0, you're just going to be left with whatever that a value is, which was 2. And if x is 1, you can think of it as 2 times whatever your b value is. So that would be 1. So when you graph these, start at 0, 2, and then at 1, 1. Again, our asymptote has not changed. You can assume unless it's shifted, so unless there's a +1 or a -1 behind it, your asymptote is going to be y equals 0. Start from here and go up. So again, domain, -infinity to infinity. The range, we start at 0, start at 0 and went up, so it's just 0 to infinity, and our asymptote is still y equals 0. Now we can still have the situation like in part B here, where our a is negative, and that is going to change our range a bit because everything's going to be flipped. So here when x is 0, remember it's just going to be 0, comma, -3, not 1, sorry. And that's because, again, when you plug in 0 here, that's the same as -3 times 2/5 to the 0, which is just the same as -3 times 1. when x is 1, you can think of this as the a term, so -3 times whatever your b term is, which would be, I guess, -6/5, which I did this ahead of time. This is about 1.2, -1.2 for when you're graphing. So 0, -3, and then 1, -1.2, so about there. So in terms of this being an exponential decay or growth function, it's a little funny because technically it is growth, but it's growing at a shorter or a lesser amount. So I've seen it both ways where people still say this is exponential decay or they say it's exponential growth. I would call this exponential decay just by the idea that your b term here is between 0 and 1. But in terms of our domain, it's still -infinity to infinity, and our range is, now careful here, this is flipped. It starts at -infinity up to our asymptote, which is 0. So this is that flipped one where it's -infinity to 0. That's always going to be the case when you have it flipped over, so when your a is negative. And then the asymptote is y equals 0. Okay, so just like last week, we also are going to shift these. So the steps for this is that you're going to start with the parent function. And remember that parent function is what we just graphed just in this last example. It's your y equals a times b to the x. And then you're going to move your points. So move points. And just graph those 2 points by transformation, whatever that transformation is. And the rules are the same as last week. So if you have y equals a, b, x, and then it's minus h plus k, the minus h is going to move right h, however many, k is going to move up k. Then you could also have, if you want the other version, it's y equals a, b to the x plus h plus k. Oops, minus k. I want to go the other way, sorry. Minus k. So this would move left h and down k. So that rule is still the same. So I'll run through these examples and then you can start on your work. So again, start by graphing just the parent function. So I'll do that in red here. So we have y equals 4 times 1/2 to the x. So at x equals 0, again you can follow that rule. It's going to be 0, comma, whatever your a is, so 4. And at x equals 1, think of it as 4 times 1/2. So it'd be 1, comma, 2. So these are my original points that I'll graph, and then your asymptote is originally at y equals 0. So I graph at 0, 4, and at 1, 2. All right, and now we do our transformation. So this had x plus 1. So we had y equals 4 times 1/2 to the x plus 1 minus 2. So that plus 1 means left 1, and the minus 2 is down 2. So each point needs to move left 1, down 2, left 1, down 2. And then don't forget the asymptote also has to move. It doesn't really make sense to move it left 1 just because it's a line, but it does have to get moved down 2. So our asymptote is now here at y equals -2. And our points are now there. So when we graph this, we approach the asymptote, but again, we never touch it or never cross it. So our domain is -infinity to infinity. But the range has changed. Now our minimum is at -2 up to positive infinity. So -2 up to infinity, and the range is y equals -2. If you're feeling happy at this point, you can go ahead and stop, but I'll do one more example in case you want to see this. So this next one, we have y equals 1/4 x minus 1. So again, the parent function here is just y equals 1/4 to the x. So at x equals 0, that would be 1/4 to the 0 is just 1, so we have 0, 1. And at x equals 1, we'd have 1, 1/4. So when we graph this, we're at 0, 1, and 1 and 1/4, so it's really close to that x-axis, which is, of course, our asymptote. So then our transformed function, transformation here, just because this looks like your go-formative. Transformation, it was y equals 1/4 to the x minus 1 plus 1. So the minus 1 up in the exponent means we go right 1, and then we're going to go up 1. So we go to the right 1, up 1, right 1, up 1. This one's a little funny because it goes past that point. Be a little careful there. And then don't forget the asymptote also goes up 1. So our new asymptote is right here. And starting from the asymptote backwards up, we go like this. So our domain here is negative infinity to infinity. The range is now 1 to infinity. It comes from that transformation, that up 1. And then the asymptote is at y equals positive 1. The go-formative looks similar to last week. There's just a space for you also to label your parent function and your transformation for the last ones that need that.